In this video, we're going to discuss linear correlation between two random variables and regression, which would be used to find a model of the relationship between two random variables. So let's get to the document. Linear correlation, we can think of a population that has several random variables in it. In other words, like a group of people. We could measure one aspect of each person that we select for our sample and a second aspect as well. And if we just have two, we can find out if there is significant correlation between the values that we measure in those people. And each individual would be a sample point, and for each sample point, we would have two pieces of information, two measurements. And so we can think of those as ordered pairs. And the relationship between them, the linear relationship, can be measured as it's called a linear correlation coefficient. In the population, we know that when it might exist, but we don't know what it is. And it's going to be a parameter of the population. And in the sample, the data we collect, we could calculate a statistic that is an estimate of that linear correlation in the population. And it is calculated from the ordered pairs that we collect in our sample. As an example, let's look at a whiteboard here. Okay. Let's say that we have a population and in that we have a set of X values and we have a set of Y values. And if they are related, linearly related, there would be what is called a linear correlation coefficient that is measures the strength of that linear relationship. And it is designated by the Greek letter rho, R-H, long O, like pronounced as the word O. Okay? And we're going to collect a set of ordered pairs for our sample. And so in our sample, we have a set of X's and Y's, and we're going to treat them as ordered pairs. For each X, there is a corresponding Y. Think of a person whose weight has been measured and whose height has been measured. And we have a set of these. And we could calculate a linear correlation coefficient in the sample, and we're going to call that R. And so R is an estimate. It estimates rho. It estimates the parameter in the population. So what we're going to do now is we're going to determine if there is significant correlation in our sample data. And we're going to then try to come up with a model for this data. Hang on a second, let's get back over to the document. And we're going to, once we have a model, we're going to try to use that model for prediction purposes for a given X value that it was not in our sample data. You know, we want to know what the corresponding Y would be. So we would use that model to do that. We would put the X that we have given to us into the model, and out would pop a prediction for Y. And we're going to call those predictions Y hat, but we'll get into the predictions here shortly. So meanwhile, let's first look and see what are the properties of this linear correlation coefficient. For one thing, it can only take on values between -1 and 1. -1 would be perfect negative linear correlation. +1 will be perfect positive linear correlation. And any value in between those would be a measure of linear correlation. And one of them that we're interested in is 0, which means that there is no linear correlation. So let's take a look at at some data and how that might be interpreted as a particular value of linear correlation. So let's go look at the calculator. And I have a little program here that is not on your calculator, so don't worry about where it comes from. All I'm using it for is demonstration purposes. You would not have to do any of this. So I'm going to run the program. And I'm going to tell it how many ordered pairs we want. Let's say we're going to do 50 of them. So we would measure 50. We would select at random 50 individuals. We would measure their height and their weight and come up with 50 ordered pairs. And if we were to plot these things, we would get an idea of what kind of relationship there might be between the X's and the Y's. And what I'm going to do here is, in this program, I'm going to basically control what the actual linear correlation is by giving it a number somewhere between -2 and -1 and 1. And I'm going to start out by looking at what if there's no linear correlation in the population. Okay, so remember, we're randomly selecting a set of people, and we're measuring a couple of things for these people, and there are some errors possibly built into this, so everything is not going to be perfect here. So I'm going to select number 1 here. You don't need to worry about what that 1 represents. It's just basically how I'm going to present the data. So I enter that, and here is a set of ordered pairs. You'll notice that up here we have a person who, say this is height and this is weight. They're very tall, and the weight is kind of in the middle. Same for this one right here. And then here's a person who is very short, and their weight is somewhere around in the middle of all the data too. So there doesn't appear to be any shape here, so it's rather amorphous. Okay, it doesn't appear to be any kind of a relationship between the two variables, X and Y, between, say, the height and the weight. So if we did this again with 0, which I'm going to do, if we did this again, we would see another set, amorphous set here, if the population linear correlation coefficient was 0. But it would look different. It would be amorphous and kind of scattered around here, but it looks rather random, and it would look random as well, but it wouldn't be the same ordered pairs, okay? Because we selected those at random. Okay, so let's hit enter, and then, what are we doing here? Okay, this is the sample estimated linear correlation coefficient. Remember, in the population, it was 0. in the sample, it is not anywhere near zero, but it's not extremely large either. It's negative 0.271, okay? So let's do this one more time, and we'll do it again. And we'll do 50 again. We'll set the population linear correlation coefficient to 0. And let's see what we get here. Again, an amorphous group of data values, okay? And so I'm going to, and now we get, remember, rho in the population was 0. The estimate of rho from the sample is 0.09. And it's positive in this case. But if we did this many, many times, we would see that most of the time, this estimated value of rho is going to be close to 0, either in the negative direction or positive direction, but it's going to be close to 0. Let's see what other kinds of situations we might see here. So let's go ahead and do 50 more. And we're going to set rho at positive 0.75, which means it's positive linear correlation. And again, we'll do the number 1 option. And notice now there appears to be somewhat of a pattern here, somewhat of a relationship. And it is a linear relationship. As X increases, so do values of Y. Over around in here, we have smaller X's and smaller Y's. And up here, we have larger X's and larger Y's. And as X gets larger, so apparently does Y. So it appears that there is some linear correlation here, a positive linear correlation. And I might as well at this point introduce a concept here. We want to measure that correlation, and that's what our R is going to be. But we want to eventually come up with a model of this. So we are going to basically fit a straight line through there, find the straight line that it best fits this set of data. And then we're looking to use that for prediction purposes as well. All right, so let's, there, and remember it was 0.75. The estimate from our 50 data points or 50 order pairs is 0.838. And the larger the sample size, the better this is going to be, or the closer this is going to get to the actual value of the correlation coefficient. Now let's take one more gander here at 50. And we'll set rho at negative 0.75 and see what the data looks like that we get out of the population. And we see that, again, it has a nice linear shape to a nice linear pattern here in the sample, and which is what we would expect if the true population linear correlation coefficient was large in the negative direction. And this is negative correlation. As X gets bigger, Y gets smaller. Up here we have small X's and large Y's. Over here we have large X's and small Y's. So they are in kind of an inverse relationship. As one changes in one direction, the other changes in the opposite direction. All right, let's do, and it was negative 0.75. So our estimate of rho in the population, R in the statistic R from the sample is negative 0.817, not too far off from the actual population linear correlation. Okay, so let's do one more, actually two more quickly. Again, we'll do 50. Let's let rho be close to its maximum, 0.95, and see what happens here. And we'll do this. And it gets in a much tighter pattern, linear pattern. Let's do one more, and we said 0.95. Well, we got a very, very close to the population. Our estimate is very close to rho. Let's do one more. This time we'll let rho be, we'll use n as 50. We'll let rho be -1. That's the smallest it can be, okay? Let's see what happens. Indeed, it becomes a straight line pattern, okay? So the tighter this pattern is closer to the straight line, the larger the correlation, linear correlation coefficient is going to be. Our estimate, which implies that the linear correlation coefficient back up in the population is also going to be close to a straight line. Okay, so let's back out of this. Come back to our document, and let's talk about some more what we're going to be doing here. All right, so, and this document, by the way, is online, so I want you to take a look at the causation versus correlation statement in here. Basically, there's an example here that I alluded to up in this first paragraph. If we're collecting values of two random variables at the same time, we might collect height and weight of individually selected people, or we may measure something like weekly ice cream consumption versus sun lotion consumption or sun lotion sales. Okay, those might be positively correlated, but ice cream sales does not cause if ice cream sales go up, that doesn't cause sun lotion sales to go up. There's something else involved that wasn't measured. And most likely it would be something like temperature. What is the outside temperature? If it's high, then ice cream sales will probably go up, and so will sun lotion sales go up. That would be the causation would be temperature versus ice cream and temperature versus sun lotion, not ice cream versus sun lotion. Okay, so let's see what we're going to do here. All of our problems are going to involve some or all of the following things. If we get a set of ordered pairs given to us, and every one of the problems is going to give us that information, a set of x's and a set of y's. Ordered pairs, the first ordered pair would be 7.8, 9.6. Second would be 2.5, 6.5, etc. Things we're going to do. We're going to visually examine the data, similar to what I've been showing you. We're going to take the ordered pairs and we're going to plot those. And then we're going to, skipping down to the third item here, we're going to do a hypothesis test of linear correlation. And we're going to set up a hypothesis that the correlation, there is no correlation. In other words, the correlation is 0. And if we get significant correlation from the measured, or rather the computed R from the measurements, if that is significant, then what we're going to end up doing is rejecting the null hypothesis of equality. In other words, we're going to say, we're going to reject that the claim that the linear correlation is 0. We're going to say there is linear correlation, significant linear correlation. And if that is the case, we're going to try to use the model that we come up with to make predictions for a given X. What is the corresponding Y that we would expect to see? Now back to number 2, the second item here. the central part of everything that we're going to be doing is kind of come from the Lin-Reg t-test. It's a hypothesis test on the calculator under stat tests, Lin-Reg t-test, and it is going to give us some important information. It is going to calculate for us the sample linear correlation coefficient R, and at the same time, it's going to give us a t-test statistic. It's going to give us a p-value, and it's going to give us the linear equation model of the form y hat, which is an estimated y, is equal to a constant value, we'll call it a, and it's called a in the calculator as well, plus a coefficient b of x, basically the slope of the line. And so the equation is y hat equals a plus bx, and it's going to give us that information. So the Lin-Reg t-test gives us everything we need. We just need to make use of this information to come up with well, answer the question, what's the test statistic value, and make a decision and state a conclusion. So the first thing we're going to have to do, whether we run the Lin-Reg t-test or not, we still have to put the data into the calculator. So we're going to create a scatter plot of this data. Now, on the test, you're not going to have to create scatter plots. We'll make the assumption that there is nothing in there that precludes us trying to fit a straight line model to the data. Okay? In other words, maybe those ordered pairs in some cases might look like a parabola, which is a curved line, but we're going to assume that that's not the case for all of the problems that we do, okay? On the test especially. So we need to put this data into a calculator. We need to put the X's in list 1 and the Y's in list 2. We've done this before. I think you know how to do that. You're going to go to Stat, Enter to get to the lists. You're going to clear out L1 and L2 if they need to be cleared out. And you're going to put the numbers into those two lists. And then do second mode to get away from the list. So scatter plot, how do we do it? We put the order pairs into the lists, okay? And we're going to examine the data. All right, so we make sure we clear the lists if they need to be cleared. We enter the X's into L1, the Y's into L2. In some cases, we may have to turn other things off because when we do the scatter plot, it's basically graphing, and anything else that is turned on for graphing would have to be turned off. And these are the keystrokes that you could use if you needed to turn off anything else. If you need to turn off any plots that are turned on, this is what you would do. Second, y equals, hit number 4 and hit enter. If you need to turn off any equations that are set to be graphed, you're going to do vars, right arrow to y vars, hit number 4, hit number 2, and then hit enter. And everything will be turned off. Then we need to set up a plot, okay? We need one plot on and nothing else. So we're going to go to second, y equals, hit number 1, and that would be the first plot, and we'll select plot, it selects plot 1. Actually, what I'm going to do here is go through the process on the calculator for setting this up. So let's go ahead and back to sharing calculator. Oops, I'm going to stop sharing. And go to the calculator. I'm going to clear this out. Actually, I need to quit this program. 0, enter. All right. Second, to get to plots, we're going to do second y equals. And it shows us the 3 plots. We are going to use plot 1. So I'm going to hit enter. Or I could have hit number 1. we need to make sure that it is turned on. And right now it is turned on because on is highlighted. So if this were turned off, we would have put the blinking cursor over on and hit enter so that we get that highlighted. So it's on now. And we're going to go down here and we're going to select one of these plots here. And first one is the scatter plot. This is the one we want. So if it is not highlighted, it is highlighted right now, so we don't have to change that. But say it was a histogram. Histogram was highlighted before. We would put the cursor over the histogram or the scatter plot symbol and hit enter. Then we're going to go tell it where we put the X's and the Y's. So I did it in list 1, and I think I've already got the data in here. List 2. And then I prefer this mark with the little square mark. It's easier to see. And then we just quit out of here, second mode to quit, because all we're doing right here is setting up the plot. So it's all set to go. It's on, it's a scatter plot. We're using L1 for X's, L2 for Y's, and we're using the square for the mark. So second mode gets me out of there. Okay, so now let's go back to our document. All right, so once we got that, how do we go about, it's turned on. How do we go about, not turned on, but it's set up, the plot. We need to know, how do we get the scatter plot? Well, it's a very easy step. So I'm going to go back to the calculator. I probably should have stayed on the calculator. And I am going to do just a couple of keystrokes here. Okay, I got a plot turned on. I've turned everything else off. And so I'm going to hit zoom and go down to number 9 and hit enter, or I'm just going to hit number 9. So if you hit zoom and 9, apparently I don't have the data in there. So let's go look at the data. So stat, enter. Oh, L1 and L2 are off. So I'm going to clear this one and clear this one and type the data in. So let's put it in. It was 7.8, 2.5, 1.0 anyway, or 2.6 and 2.6 and 5.6 and 1.7 and 6.1. Okay, so now let's go over to the other list, 9.6, 6.5, 1.3, negative 3.2. I'm not sure that's, yeah, negative 3.2, 6.1. And 0.9, so just 0.9, and 6.3. Okay, so now everything's set up. The plots, the data is into lists, and the plot is set up. So now I'm going to do zoom number 9, and here is our data. Okay, so we visually examined this. We determined that well, there doesn't appear to be any curved shape to it. It doesn't look like you know, because of those 2 points up here. They're not close to a straight line that would go through all of these, but still we could try to fit a line to this and see if we have significant linear correlation. Chances are this is not going to end up being significant. So, but we need to find that out. So let's quit out of here and come back to the document. And now what we're going to do is we'll, of the three things, of the things that we're going to do, we're going to run the Lin-Reg t-test next, okay? Lin-Reg t-test requires that we know where the lists are, and it requires that we use an assumed value of rho at 0, because basically in these problems we are assuming that rho equals 0, which means no significant linear correlation. And then the claim will end up being that there is significant linear correlation. And if we reject H0, we're saying there is significant linear correlation. If we fail to reject H0, we're saying that there is not significant linear correlation. Okay, so let's take a peek at what we would do for the Lin-Reg t-test. It's a test, just like t-test and one-prop z-test, etc. It's in stat tests. So we're going to tell it the information. Where's the x's? Where's the y's? This frequency will always be 1. And we're going to make sure that not equal is selected here. So put the cursor over that and hit enter. If it's not highlighted, leave the regression equation blank. We're not going to use that. And then we'll go down to calculate, and we'll get all this information out. Okay. So I did do this. I should be all ready to go. So just to make sure, let me take a peek at, let's do the calculator here. I'm going to quit out of this. I'm going to go to stat, right arrow to tests, and Lin-Reg t-test is way down at the bottom. So I'm going to arrow up to get to it, come in from the bottom. And Lin-Reg t-test is this one right here. Do not get it confused with Lin-Reg t-int. Lin-Reg t-test. So I'm going to hit enter. And list 1, list 2, frequency 1, not equal 0. Leave that blank and calculate. If there's something there, just delete it. Hit the delete key or clear it to get rid of that, okay? So we're going to go down to calculate. And our data is in the lists already. I put them in there. I know I did because you saw me do it. And we hit calculate. And here is the first batch of data. And we'll go through the important ones here, and you need to make sure that you understand which ones are important so that you know where to look for these things. All right, so we're going to go down to, there's more down below, but the R is the last thing. All right, so let's start at the top. Not close to the top. Well, actually, let's start at the top. Here's what the form of the linear equation is. This is what our ultimate goal is, to come up with an equation that fits well enough for us to use it for prediction purposes. It is a plus bx, and it actually should be y hat equals a plus bx. Estimated y's are going to be a plus b times the given x value, okay? The test statistic, there are two test statistics here actually, and we're going to go through the hypothesis test here shortly for each of those. The first one is a t with n-2 degrees of freedom. If you ask for the test statistic, this is what you're going to give it. Okay, just round it to the correct number of decimal places. Say for 3 decimal places, this would be 2.534. And the p-value is to 4 decimal places, 0.0522. Okay, And by the way, in all the problems, we will be given a significance level. So we'll know what to compare the p-value to. And most of the time, it's going to be either 0.05 or 0.01. All right. Now, what else we got here? All right. Well, we've got A and B. Well, see this model up here at the top, A plus BX. That constant in the model is this number right here. This coefficient of X in the model is this number right here. So to 3 decimal places, A would be 1.27, actually 280, rounded to 3 decimal places. And that was negative. I'm sorry, B is, I looked at the wrong one. A is negative 1.062 and B is 1.280 times X, okay? A plus BX. All right, last thing we're gonna look at here is down at the bottom, R. Okay, so, and R is the sample linear correlation coefficient. This is the number that estimates the linear correlation coefficient rho back in the population. And I'm going to look at, just for the heck of it, write down 4 decimal places here. R equals 0.7499. Okay? Those are the important things that you need to know out of the results of the Lin-Reg t-test. Oops, I did it again. All right, so stat, let's go back and just, I'm going to run the test one more time. The important things are the test statistic T, the p-value, which you'll use to determine if there is significant linear correlation, A and B, which is the model, and finally, R. So those 5 things, test statistic T, p-value, P equals, A and B for the model, and R. Okay, so let's get back out of here, come back to the problem. Or rather actually you were using a prompt where I think I gave a, probably not, okay. Anyway, that's how you're going to input data into the Lin-Reg t-test. It's pretty simple. And this is what you're going to get out. And remember, you need T, P, A, B, and R. Okay. Now, how do we do a test of significance here? 2 ways. Let's look at the p-value approach first, which is the one you'll use most of the time. Our claim in all of these is going to be that there is significant linear correlation. In other words, that linear correlation coefficient back in the population is not 0. Okay? If it were 0, that would be no significant linear correlation. If it is 0, if it is 0, there is no significant linear correlation. If it's not 0, there is a significant linear correlation. If rho would be, if it were positive, it would be positive linear correlation. If it were negative, it would be negative linear correlation. But 0 is no significant linear correlation. Okay, so H0 is always going to be rho equals 0. This is what we're rejecting or failing to reject. All right, so if it's like the alternate is not equal 0. Okay, test statistic, you don't have to worry about where it comes from. Just know for you, it's going to come from the Lin-Reg t-test. Okay, the p-value comes from the Lin-Reg t-test. How do we make our decision? We have a p-value. So we use the p-value, we compare it to alpha. If it's less than or equal to alpha, we will reject H0. But our p-value was 0.0522, and let's assume for the moment that the significance level was 0.05. 0.0522 is greater than 0.05, therefore we will fail to reject H0, okay? And in our conclusion is going to be, there is not sufficient evidence to support the claim that there is significant linear correlation, okay? We remember what happens here. If we reject, we are supporting the claim in this case. If we fail to reject, we can't support the claim, okay? That is how, basically, it's going to be written in like that. Do we have significant linear correlation or not? Okay. So let's continue on. That's the approach we're going to take using the p-value approach. Everything just basically comes from the Lin-Reg t-test. Now, if we are going to use the critical value approach, okay, that R that we got from the Lin-Reg t-test, that is the other test statistic. If we want to use, it is what we would use if we were going to use the critical value approach, okay? So if the, where do we get the critical values for this thing? Well, if you look at this little picture right here, the distribution of R when rho equals 0 in the population, R most of the time is going to be close to 0, as I showed you when early on when we looked at the calculator and did scatter plots. So most of the time R is going to be around here. But if R is significantly different from 0, remember it's an estimate of rho. And so if R is significantly different from 0, we're going to reject H0 in either direction, significantly negative or significantly positive. What we do need to know is what are the critical values that are going to tell us how far it has to be to the right or how far it has to be to the left in order for us to reject. So we are going to go to table A6 in the Formulas and Tables handout to get those. And we need two pieces of information there. We need to know what alpha is, and we need to know what the sample size is. There are no degrees of freedom for doing it this way, doing the critical value approach here. Okay, so let's take a peek at what we've got here. Right here. All right, table A6. I think it's like the third or fourth page. Third page in the Formulas and Tables handout. And it basically has two columns of critical values. One, if we're going to use this column if alpha is 0.05. We'll use this column if alpha is 0.01. So it's undoubtedly going to be one of these two significance levels if we are asked for critical values. So we're going to go down this column, and in our little problem that we're dealing with right here, if alpha is 0.05, we're going to go down this column, and then we're going to go to the sample size row. And we had 7 values. So we're going to go to the 7 row, and the critical value is 0.754. okay? So that's how we're going to use this table. If we need a critical value for test of correlation, we're going to use table A6, and we're going to look for the column that corresponds to the significance level, and we're going to look in the row that corresponds to the sample size, the number of ordered pairs. Okay, so let's stop that and come back to our document. And so for our little problem, the setup is exactly the same. We're always going to say that there is significant linear correlation in the claim. There is not significant linear correlation in the null, and that there is significant linear correlation in the alternate. Okay, so if we, and again, if we reject 8,0, we're basically supporting and saying that there is significant correlation. If we fail to reject 8,0, we're saying we can't support that linear, significant linear correlation. All right, so since this is a two-tailed test, we might end up with an R that is negative or an R that is positive. Well, we're not going to worry about whether we are looking on the left or the right. Notice that in table A6, all those critical values were positive. All we're going to do is use the absolute value of R and compare it to the critical value. Absolute value of R basically just changes a negative to a positive. So if R is negative, we'll use the positive. If R is positive, we're still using the positive. And we compare that. If R is greater than the critical value, we will reject 8,0. That's the rule. You got to remember that. If R is greater than the critical value, we'll reject 8,0. So our value of R was to 3 decimal places was 0.750. And it was positive, so we don't have to change the sign. It's already positive. And it happens to be smaller than 0.754. Okay, it is not bigger than the critical value. It is smaller than the critical value. So we're going to fail to reject 8,0 for our little example. And of course, if we fail to reject, we're going to conclude that the data does not support a significant linear correlation. Okay, so now what are we going to do for predictions? All right, that model that we came up with, negative 1.602, or negative 1.062 plus 1.280, that model times x, that model is the best straight line to fit through that set of data, but we rejected 8,0, which means that we cannot use the model. If we reject 8,0, we cannot use the model for prediction. Okay? If we reject 8,0, we cannot use the model for predictions. So, but if we had not rejected, then we could use the model for predictions, but we have one more restriction on here. And it's all of it, this is summed up in this table, okay? We take the A and the B that we get from the Lin-Reg t-test, we put them into this equation, and that becomes our model. If we can use the equation, we substitute the given X into the X location, evaluate this, and the value that we get from that is the prediction of Y for that given X, okay? So if we reject 8,0 and the X that is given to us is within the bounds of the sample X values, and let's go back and just take a quick peek at what those bounds were, okay? The bounds, what's the smallest sample X? 1. What's the largest sample X? 7.8. If X is between those, inclusive, we can use the model. and we put it in here. So in order to use the model, we have to have rejected H0, and we have to have a given X that is within the bounds of the sample X's. Okay. Notice in all, these are 4 possible situations. You reject H0 and the X is within bounds, or you reject H0 and it's not within the bounds, or you fail to reject H0 and X is in the bounds, or you fail to reject H0 and X is not within the bounds. Of those 4 situations, the only one where you can use the equation to come up with predictions is when you reject H0 and the X is within the bounds. If you reject H0 but the X is not in the bounds, we can't make a prediction. Okay. If we fail to reject H0, no matter whether X is in the bounds or not, our prediction is going to be the average of the sample Y's. Okay, so how are we going to do the average of the sample Y's? Well, we've got a little blurb here. We would do 1-bar stats on L2 because that's where the sample Y's are. So we would do stat, right arrow to 1-bar stats and hit enter because it's the first item there. Right arrow to bars. I'm sorry, I think I gave you the wrong words there. Right arrow to calc and hit number 1, or just hit enter. Okay. Anyway, when you do 1-bar stats, stat, right arrow to calc and hit enter is going to get you to 1-bar stats. Tell it second to, which is L2, and then hit enter, and then look for the X bar in the 1-bar stats output. It's the mean of that list. And since the list is the Y's, it's the mean of the Y's. And that is going to be your prediction if you need the mean of the Y's for your prediction. And remember, when you need that is when you fail to reject H0. You're going to use the mean of the Y values, sample-wise, as your prediction for any X. All right, I'll tell you what we're going to do here. We're going to go through one example, and I've got, let me stop sharing this and go find our examples. These also are included along with the solutions in the chapter 10, chapter notes, chapter 10. Okay, so let me go to practice problems. This. Let's go through this whole thing. We'll skip the first page and go to the second page, and let's do I'm going to I'm going to do number 3. Oops, here we go. Test a claim of significant linear correlation using the order pairs in the following table. Let's create a scatter plot from the data and find the prediction for the X values in the second table. I will let you do the scatter plot on your own, but you do, well, actually, let's do this. Go ahead and put the data into a list. And let me go ahead and do that. Might as well do the scatter plot anyway. Okay, so clear this and let's go to stat, enter, clear, enter, clear, enter. Let's go to this 11.3. 15.7. 13.6. 15.7. 17.5. Error, quit. All right. 15.7. And 17.5. Having trouble getting 17.5 in here. 15.8. And finally 15. All right, and then let's go up to and do the 6.1, 1.4, 3.4, 2.5, 0.3, 2.5, and 2.2. Okay, so here's our set of data. I'm going to quit out of here because I don't want to mess up my lists any worse than they are. And I'm going to go to, and I think I still have everything set up for that plot. So zoom, enter. Apparently not. Stat, enter. L1, L2. Second, y equals. L1, L2. This is still turned on. Second, quit. Try one more time. Zoom. 9. There we go. I hit the wrong button. Okay, that's what our data looks like. Looks like we got a pretty good straight line here. But we won't know if it's significant or not until we run one-bar stats. Not one-bar stats, until we run Lin-Reg t-test. All right, so let's get that done. So second, quit out of there. And now I'm going to go stat, right arrow to test, arrow up to Lin-Reg t-test, L1, L2, everything is still the same. I don't have to change anything. And I hit enter, and I get a test statistic, t equals negative 8.154. And I get a p-value of 4. Well, actually, what do we got here? E to the minus 4. Obviously, this is not a probability by itself because it's larger than 1. And so I look over here to see a negative exponent. That means I'm moving the decimal point 4 places to the left. And so this is going to round to 0.0005. This 4 is going to become a 5, and there's going to be 3 zeros in front of it before you see the decimal point. Okay, so so it appears that we're going to reject 8.0 because that's less than 0.05, which was, oh no, actually we're using 0.01. It's less than 0.01, therefore we're going to reject 8.0 and say that there is significant linear correlation. And if that's the case, looking back at our little table for prediction purposes, if that's the case, we need to use this A and B as our model, 15.855 plus negative 0.855x, that's going to be our prediction equation. And we could also look at R. R is negative 0.964. And remember that it can only go as low as -1. So that's pretty close to -1. That's getting close to perfection. In which case we would compare this to that 0.754, the absolute value of this, which would be positive 0.964. We could compare that to that 0.754 critical value, and it's greater than that. Therefore, we reject H0 for this reason as well. So we're going to reject it whether we use the p-value approach or the absolute value of R compared to that table 6 critical value with 7 or 0.01. Actually, we're using a different critical value because we're in the 0.01 column. But anyway, it's not that this is going to be bigger than the critical value on that side. Using the 0.01 significance level. So we need to know what this equation is. 15.855 plus or minus 0.885x, okay? And so let's get out of here. Oops, okay, we won't use that again anyway. And let's go back over to the problem. Okay. Our decision was to reject H0. Our conclusion is there is significant linear correlation. Now I've got the regression equation was actually, let's go look at I've got the solutions in here as well. If we look at the regression equation, 15.855 plus negative 0.885x. And if we have given values of x, 9.5, we've got a good prediction equation, or predictor equation. It's a valid model since we rejected, as long as the x is in the range of the sample x's, and 9.5 is not in the range, okay? So you'll notice that I have the mean value of the sample y's in here, but technically this should be no prediction, okay? If you remember that table, if we reject H0 and the x is not within the bounds, we can't use the regression equation. We can't make a prediction. 14.7 though is within those bounds, and so we use the regression equation, and this is the value we end up getting, 2.846. If we substitute 14.7 in here. And 18.8 is not in the range. So again, technically we can't use the equation, and technically we can't really make a prediction here. Okay. I don't think you'll run into a problem where you have to make that distinction where you reject H0 and you have an x outside the bounds of the sample x's. And I would like for you to use or do these other 3 problems here. And basically, they're fairly simple, 7 ordered pairs, and just check the notes, go through the notes, learn what you're going to do, or know how to find the scatter plot, know how to run the Lindbergh t-test, know how to put the data into the calculator first, and then complete the test, the steps in the test. All right, I think that's pretty much covers everything you need to know in chapter 10. A little lengthy, but actually there's not that much material there. I just went on and on, so that's what made it long. So good luck on those problems, and keep up with the homework.